Okay, good morning everybody. I'm delighted this morning to welcome Peter Washam. Peter was a master's student actually here in Miami at FIU, working with Rob Bergman, he just told me, and he got a PhD at the University of Delaware working with Andreas Munchau. And since 2019 he's been a research scientist, first at Georgia Tech and now at Cornell. So welcome, Peter.
Thank you.
We're excited to hear all about Greenland or ice sheets, bipolar ice sheets.
Bipolar, all of it. Thanks for coming out. I know everyone's busy. It's the end of the semester currently, so I know everyone has a lot going on. So I'm really happy to be here. I'm going to talk about ICCs, polar oceanography by ship, snowmobile, and submarine robotics, which are kind of like the three platforms I'm currently using to do my work. And in the background here, this is a photograph I took flying into McMurdo Station. And this is the Terra Nova Bay polynya, which is one of the most productive polynyas in the world. So it stays open all year long, despite temperatures -30, -40. And it's just this amazing sea ice factory that creates bottom water, Antarctic bottom water. And it's a really exceptional thing. And when we flew over it and it's wide open like this, I was like, I have to take that picture. So this was last week. I flew back from Greenland on Friday. So I'm happy to be here in the warmth. Very tired. I'm very frazzled from 6 weeks on the ice, working hard, doing a lot of manual labor, and working with this team right here to deploy our underwater remotely operated vehicle, Iceman, it's called, that my boss Brittany Schmidt right here developed with an engineering team, and I'm the sort of resident researcher working with all that. So yeah, it's a big switch. No more frozen fingertips for the next little bit at least, but yeah, I'm really happy to be here.
Please speak a little louder.
Yes, I'll try. My voice, I'm sorry, it's been a lot of traveling and a lot of hard work, so my voice is sort of
I
shy.
cannot hear you.
I'll do my best, I promise. So why do ice sheets matter? So this is an animation from NASA of Antarctica, and this is the ice flowing off the ice sheet into the ocean. The colors go from white, which is basically no flow, to orange, green, blue, purple being fast flow. And this is why it's important to study these regions, because just like adding cubes of ice to a glass of water, this is what's raising sea level. And it's responding in turn to the ocean forcing against it. So these are some helpful figures that show the size of Antarctica and Greenland relative to the United States. The largest ice shelf, an ice shelf is a floating glacier, right? So it's detached from land and is now floating on the ocean, but it is still connected to the glacier upstream, which is grounded. So the largest ice shelf in Antarctica is the Ross Ice Shelf. It's the size of Texas. So Antarctica is much larger than the US, and Greenland is about the size of sort of this portion of the US right here. This is not going to happen anytime soon, certainly, but if Antarctica were to melt entirely, it would raise global sea level by 57 meters. And if Greenland were to totally melt off, it would raise sea level by 7 meters. But they are melting and they are raising sea levels. In the past 50 years or so, Antarctica and Greenland both raised sea level by about 1.5 centimeters, which is a significant amount, except for when we look to the future. So by 2100, the projection from Antarctica is a 6 to 53 centimeter sea level rise. Greenland is 2 to 25 centimeters. This range is insane, right? Like, the uncertainty bounds on this and how do you plan for it are just really sort of stark. But I think my work has something to say about how we can reduce these uncertainties. So I'll show a video here from Petermann Glacier in northern Greenland, where I did my PhD research. that shows how the ice responds to different forcing from different greenhouse gas emission scenarios. So this is the ice, Petermann Glacier and Humboldt, and this is like a low emission scenario, a medium, and a high. And you see the ice retreating at different rates to different extents, right? So yeah, it's really something that we need to get a grasp on. So one of the problems with projecting sea level rise, especially when you think about ice melting from the ice sheets, is the actual parameterization of how ice melts into water. So this is a figure from a proposal where basically we're looking at the melt rate of an ice shelf or a block of ice, whatever you'll have under these conditions, quite cold, quite saline, under these different current speeds. And this bottom curve is a parameterized melt rate under sort of low heat flux, salt flux efficiency, and this is over a high heat flux, salt flux efficiency. And as you warm and freshen the water column, it increases. So if you were to warm from -2 to 2, so 4-degree warming, you would go from a range of melt rates, something between almost 0 to 4 meters a year up to something like 15 to 200 meters a year. And just how, depending on how you pick these three parameters, which is the drag coefficient and the heat and salt transfer coefficient, these are supposed to parameterize what's happening in the boundary layer, right? If you have a stratified boundary layer, you'll be down here. And if you have an unstratified boundary layer, you'll be up here. So just depending on that, you can have sort of a 5 times difference in melt rate, right? And these are constants as they're applied, but in reality, they're nothing. There's nothing constant about them. They're constantly changing. So one of my convictions is to fill these sort of plots out with real data that help us understand where the parameters are working and where they're not working, and to simplify observations to the point that you can integrate them into models. So just one moment. This is South Florida currently. I'm assuming some of you or most of you have seen this figure, so I won't belabor it. But yeah, under current sea level status, this is what South Florida looks like. This is it with 1 meter of sea level rise, where you're starting to see, especially the West Coast, being flooded with water. And this is it with 2 meters of sea level rise, where the boundary is actually not expanding that much with the depth of the water that's sitting on land. Now it's increasing, and you're starting to get more. I believe maybe this is Fort Lauderdale being flooded. So where do I come in? As Lisa introduced, I started at University of South Carolina. I worked with Sasha Yankowski doing undergrad research there on estuarine oceanography. He used to be at NOVA actually, but he's this brilliant sort of theoretician, observationalist, modeler, who really, like at a young sort of early career, the earliest of career scientists, like I had that impact that really, I think, set me on a trajectory that I've followed quite tightly. I then did work with Rob Bergman, focusing more on El Nino, so more large-scale climate, and then I worked on the polar research at University of Delaware with Andreas Monchow. And since then, I've been focusing on underwater robotics, first at Georgia Tech and then at Cornell. So these are my general research interests: glacier-ocean-atmosphere interactions, coastal oceanography, and then underwater robotics. And these are my different tools, basically whatever I can get my hands on to do the work I need to do. So I just came back from Greenland. There was sea ice, so ships aren't going up there, so we use snowmobiles. So you can drive snowmobiles, put holes in the sea ice, do your research that way, whether it be single CTD profiles or anything else. Remote sensing, I'm more so using it to study or monitor how glaciers are changing due to ocean conditions. I did a fair amount with moorings during my PhD, and then I also use water samples that I send off to Woods Hole to analyze for noble gas concentrations, which are an amazing, powerful tool for tracing water masses because they're conservative in the utmost sense. And then I also, I do not run models, but I work with people who run models, and I attempt to integrate our observations into those models. So most of my work, though, has been related to this robot ice fin because it's a beast of a platform that generates terabytes of data that has to be sifted through. So here's a video of ice fin under the ice that was taken about 2 weeks ago in Greenland. And it's this long torpedo shaped. It's about 3 meters by 25 centimeters across. And it has nearly all the instruments a research vessel has. It's just packaged in smaller form, and they all look sort of different or have different ranges due to the compact nature of it. So the rest of my talk's going to sort of look at the different elements of the ice sheet sea level rise narrative and how I see my research playing into this narrative and the things that I think are sort of important to me and my responsibility to work on. So first, estuaries beneath the ice, the grounding zone. So Walter Munk, actually in one of his last works, The Sound of Climate Change, discussed how important it was to study the ocean cavities beneath ice shelves in the Arctic and Antarctic, and how the grounding line was this critical point where ice meets the ocean for the first time. So this is a schematic of a glacier flowing off into the ocean. So this right here is the grounding line or the grounding zone, basically the point where the ice is first contacting the ocean. And in this sort of setting, you have a really sort of interesting dynamic that's happening where you have generally your warmest water interacting with the ice, certainly the densest water interacting with the ice. But then you have these rivers under the ice called subglacial channels, which are fed either from friction on the ice base or from surface melt in the summer that then drains down and exits through them. And you have a total estuarine environment in the setting where you have fresh water flowing out into seawater, but then you've got an ice sort of lid on it, which plays really interestingly into the dynamics. So I first kind of became interested in this grounding line or grounding zone setting during my PhD. This was from a paper in 2019 where we went to Petermann Glacier, and there's this channel, you can see it in the surface. And we drilled through that channel in the ice shelf, so this part's floating, this part's on land, that's the grounding line or grounding zone. So we drilled through it with a hot water drill, and deployed moorings through it. And there was 3 of them, 16, 26 kilometers from the grounding line. And what was really interesting there is you would get these pulses of meltwater passing these 3 sites. So you can see them. This is now a meltwater fraction that's been calculated. You can see these spikes happening at each one of these sites, right? They're really sort of strong and apparent at these locations, and they're happening during neap time. Not during the springs, but during the neaps. And I had no current meters, so we used time lag cross correlations and phase lag partial coherence tests to figure out that the water was actually flowing out from the grounding line. So that was basically what piqued my interest, because I wanted to know what was happening here and why this was only happening at neap tide. So this is sort of just going back to the grounding line in a schematic form and sort of drawing us back to what could be happening to cause this sort of periodic outflow. So this is Biscayne Bay. This is a schematic that shows just classic estuarine 2-layer circulation. You have fresh water flowing out above and you have seawater below. And this is a proposal figure. showing that in this sort of grounding line or grounding zone region, you have a similar scenario where you have red being seawater and light blue being freshwater, and you have sort of a potential two-layer circulation. But now you have an ice shelf above it, and so when you eject freshwater into this environment, if you have an interface that's sloping upwards, your freshwater can destabilize instead of stabilize, because it will rise and mix as it does. Whereas in a scenario where you have sort of a flat surface, there's waves here, but you could assume it to be flat, then that source of buoyancy is a stabilizing force once it reaches that point. So yeah, this is just sort of to point out that these two environments or settings are quite similar. So my first opportunity to work with actual grounding zone data was at the very chill, relaxed, not politically sort of stressful Thwaites Glacier in Antarctica. So this was a part of the large International Thwaites Glacier collaboration. This was the field team who went down there that year. I actually wasn't there for this. I was on the other side of Antarctica at the same time in the Ross Sea working with a New Zealand group. But they collected these amazing data, and it was my opportunity and privilege to be the main person to work through the underwater robotics data from Iceland. So this is a figure from this paper published in Nature, where I basically co-wrote it with my supervisor. And this is the Thwaites Glacier grounding zone. So this is our map. This is the eastern ice shelf of Thwaites that's still intact for now, but breaking up currently. And all the data comes from this little red box right here. So this is now showing there's these two tracks, this track 1 here, this track 2 here, and they're approaching, this is now a shaded sort of grounding line or grounding zone. And you can see now the data plotted up where gray is ice, brown is seafloor, and this is now ocean thermal driving, which is temperature relative to freezing. And so the water is quite warm. I should point out before I go any further, at track 2, they actually hit the actual grounding line, like ice, seafloor meet. It's like a feat, right? Like that doesn't happen. Like this was one of the first times anyone's ever observed that. But generally speaking, and we're oceanographers, we care more about the water anyways. The water was warm at depth and it cooled towards the ice base. And there was this really bizarre and rugged ice topography that didn't really look like the schematic I showed before, where you had really big crevasses. You had these things called terraces, which are like these step-like things. You had this sort of corrugated rough ice, and then you had these grounding zone wedges formed by the retreating ice. But then, in a companion paper that I was co-author on, and this was my responsibility and role with this paper, was to analyze the ADCP data from our platform. So this is the same, basically track 1 and track 2 here, track 1 and track 2, now plotted with the ocean currents underneath the ice. So anyone who's worked with ADCP data knows how hard it is and messy from a stable platform. Now take it from a 3-dimensional moving platform. And it took 6 months to get this result, but now I think I have it where it's more or less plug and play. But the takeaway here is that there's this sort of slow current speeds, and they're mostly going into and out of the page. So a coastal current in this scenario, not a back and forth sort of typical inflow, outflow, 2-layer estuarine thing. There's still like a reversal here, where this is the blue is going into the page, the red is coming out of the page, and there's some other interesting dynamics with sort of Ekman layers and whatnot. But one of the key takeaways was there's flow concentrated along this wall of the crevasse here. And that's where we found the strongest circulation. So that was a big result that helped us understand better what's happening in these grounding zones. So at the same time, we were at a different location in Antarctica. This is the Ross Ice Shelf. This is the grounding zone of Cam Ice Stream. So this is from a paper that Justin Lawrence, who was a PhD student at the time, wrote, and I was sort of second on that paper. This is us in the field. This was 5 years ago, right before COVID. But we saw a similar environment in that you had very stratified water columns. So yellow here is the warmest water, purple is the coldest, and there's this really nice picnic line. It's shown as a thermocline, but it's indeed a picnic line as well. So the water is much colder here, which is why this ice shelf isn't melting nearly as fast and not making headlines. But it was actually even sub-freezing in some locations. You have these big crevasses spaced in the same way. There's some asymmetry, and then there's this really cool dive, the last dive we did, where we took the robot into this crevasse on either side and mapped the circulation and hydrography in it. So I will just take a sip of water real quick. So I think this is probably one of the figures I'm really proud about. It certainly contains a lot of information, so I'll do my best to sort of make it digestible. But what we're seeing here is a crevasse, that same crevasse I highlighted. This is now the binned ocean temperature relative to freezing on either side from the vehicle. So that's shaded here. And then this in the beginning, or in the middle, is the currents going into and out of the page from the ADCP. So this is basically a V velocity. And what we found here was that the primary flow, once again, was concentrated in this crevasse, and it was flowing sort of through it into the page. So in this sort of southward jet. And then the rest of it was sort of this sort of messy, non-coherent stuff. So it gets more detailed. I'm sorry, it's a lot to digest, I understand. But basically, now I'm plotting the U velocity, so left and right, and the W. And again, this is all coming from our three-dimensionally moving platform. And so there's this awesome overturning circulation that we observed, once again, where green is rising and purple here is sinking. And these white lines are the supercooling horizon. And these white lines show where the water, the ocean water, is now drop below freezing and is actively forming frazzle ice. And when that happens, releases salt, essentially, and it's densifying the water column. So you had this really cool, like, sinking plume, which was a result from the most intense supercooling up here. And that was driving this really neat overturning circulation that was overlaid on this through-flow jet. And then the circulation, basically, that downward sinking plume was also sweeping away from the wall some. And there's basically no other lateral flow whatsoever in there. And not surprisingly, this sort of stuff isn't included in idealized models that are feeding forward into melt rate parameterizations and modeling of large-scale melt in Antarctica, partially because this was the first time we observed it. So going back to estuaries beneath the ice, this is now results from one of these channels flowing out into the ocean that I mentioned earlier, where you have fresh water discharging into the ocean. It's a really unique environment that, if I have time later, I can talk to you about more. But for the fact of this, I'll just sort of point out the strength and the capability of using noble gases. So this is a result from this project that I co-PI'd, which is coming to an end this calendar year. But this is a paper that's in preparation. I had hoped to submit it, but then fieldwork took over my life. And as you all know, it becomes harder and harder to finish papers the more busy you get with all the other stuff. But just to highlight what we're seeing here, these are fluxes through this channel. These are the two sort of sources of fresh water. This is subglacial fresh water. This is the stuff generated upstream on the grounded ice. And this is the stuff generated by the ocean melting the ice. So we have this detached plume basically flowing out at mid-depth in this very large cavity underneath the ice. And then you have this really neat inflow at depth of seawater coming in, and there's like what seems to be almost like a trapped bottom boundary layer there. And so the ability to partition data like this into the different water masses, the different sources of heat, all result from these stars where we took water samples and had them analyzed for noble gases and helium isotopes. There's just super powerful tool that then you can correlate with just typical temperature, salinity, oxygen data to sort of fill out these vertical profiles. And they're even powerful enough to identify volcanic heat sources. So actually there's a source of heat upstream of this that's generating meltwater through volcanic heating of the ice. And we have an area heat flux from that, which is another sort of novelty of working in these environments. As I mentioned before, my life got taken over by fieldwork. This is fresh data from the field. On the right here is Rasmussen Glacier in Greenland. This pink track shows our vehicle track from a couple weeks ago, where we took the robot underneath the ice all the way past what should be the grounding line. And this is kind of like just what we get spit out the next day to quality check the data, where the light blue is the sea ice, the darker blue is the glacier, the brown is the seabed, and the stuff that's washed out that you can't really see is the sediment load. This is raw turbidity in the water column, and you can see there's some signal that then really gets dark at this point where everything collapses. So this is another one of those subglacial channels, and this is now for a much smaller glacier in Greenland in the winter, where we took the robot upstream of the grounding line in one of those channels. So this is a screenshot from our forward-looking sonar on our robot. So this is how we drive in these really sketchy scenarios, where anything that's bright is basically a reflector off the ice. And so you see the opening to the channel there, which is only about 15 meters across, maybe the size of this room. These are the two walls of that channel, and the vehicle is pitched up slightly, so you're actually catching the roof of the channel here and here. And so these videos are hard to interpret a little bit if you've never looked at them, but I'm gonna play it just to show this is what it looks like to collect these sorts of data. And you can see as we're driving the robot in, this channel is narrowing further and further. And then my boss, Brittany, was actually driving along the wall at this point, and you can get some idea of the texture and morphology in the ice that you can then combine with visual imagery to actually understand the mixing processes happening there. So just some ongoing collaborations focus on these sort of settings. This is Veronica Hegelin, she just completed her first polar fieldwork season. She has a paper in prep. It should be submitted hopefully in the next couple months, focusing on a grounding zone in Antarctica. And this is Will Scott, who's a PhD, a postdoc in Australia. But during his PhD, he developed a model, a finite element model called Fire Drake, that takes real topography in the ice and the sort of observations we're gathering with our robot to model these grounding zone environments in a way that's more realistic. And so him and I are still talking back and forth, and in his spare time, he's working on producing a manuscript at least on that stuff. So future opportunities. This is where I was in Greenland most recently. So this is Westernholm Fjord. These were the sites we were at. This is the Pacific Space Base where we stayed, which is a military base. So it was dual funded. The Heising-Simons Foundation funded a project that took us up there, and then NASA funded the other project. And my supervisor or boss, Brittany Schmidt, is a planetary scientist. So NASA loves this stuff because it's really it resembles things you see on Europa, and it has some analog sort of comparisons that you can make to Europa that they then really sort of people like her can make to sound like really compelling science. So we have 2 more seasons up there, the next 2 springs, so same time of year. I'm going back to Petermann Glacier in summer 2026, which is really exciting. So a big UK grant called, it's called GRAIL, but it's funded through the ARIA funding solicitation just came through, and they're like fast tracking this work to happen up there next summer. And then I submitted a pre-proposal to the Heising-Simons Foundation to fund our part of the work, which in May I will sit down with them to talk through further. And then there's some work I also have funded to continue in Canada on Ellesmere Island on the northern coast. So I got a rapid grant to send someone up last summer to collect noble gas samples, like what I showed, all through here. And the logistics are more or less taken care of, so it's an open invite, so long as you can fund someone to go out there, and that's just continuing forward. But that grant, since it's a rapid, is a 1-year grant, and it's coming to a close at the end of the calendar year. So, just to summarize, grounding zones are these thin water columns that experience estuarine mixing dynamics, and they're just really uncertain variables. When you start thinking about a warming ocean or warming atmosphere, you're generating more fresh water, and we just don't have a great grasp on how they're going to behave moving forward. So the next part of my talk is focused really on these small-scale interactions at the ice-ocean interface, which are happening in the boundary layer, and how important they are for large-scale climate. So here's a schematic showing, it's actually sea ice in the schematic, but you can think of it as just a flat piece of an ice shelf. And this is a boundary layer. Basically, you have sort of an outer layer where you have turbulence dominating mixing, and then you have the super thin, and actually this would probably continue into the surface layer. But then there's this viscous sublayer that's the super thin millimeters to centimeters scale feature where you're only moving heat and salt from molecular diffusion. So that can be flipped on its side now. If you were to have a crevasse or a large glacier that's calving, and then any fresh water you're generating from melting, instead of being like a stabilizing force in here, that buoyancy would then destabilize as it rises and then becomes turbulent. So there's ways of parameterizing these sort of mixing processes across the boundary layer. This is one of them. This is, you're then calculating here a heat transfer velocity, a salt transfer velocity. Everything in yellow is due to turbulence. Everything in light blue is due to diffusion, molecular diffusion. And most models just boil this down into these constants. These constant parameters that then are just applied at sort of large scales. Whereas in reality, none of this is constant whatsoever, because you have a drag coefficient, you have varying current speeds, you have things of that nature. So going back to this figure, I think it's important just to point out, like, once again, based on published observations, when you take these parameters, the low bound and the high bound that you can get in estimated melting, just because if you're considering sort of a stratified in boundary layer where you have density inhibiting turbulence, or an unstratified boundary layer where heat and salt can just run right into the ice and melt it. And that's really leading to this large spread in these sort of projected melt rates. So during my PhD, I got my first opportunity to work with this sort of these sort of physics. These are boundary layer profiles from those same sites that I showed earlier beneath Petermann Glacier. This is thermal driving, so temperature relative to freezing. This is salinity, and that's buoyancy frequency. So this is like a mixed layer, an under ice mixed layer. And then you can see, like, really close to the ice, there's something that's happening with salinity where it seems to really dive off, but we can't really resolve anything closer than that, or we couldn't at the time. And then there was these moorings that were deployed underneath the ice that then the ice melted away from. So it's pretty evident that there's some turbulence going on there, and then there's something happening here that we have no clue about. So the basically focusing on these two sensors and these two sensors, I basically got to take a look at the dynamics of melting that was happening in that boundary layer. And this is one of those really sort of data-rich figures that I'll try to make it easier to look at. So the first thing, this is the melt rate as measured from a phase-sensitive radar. Basically, you put a radar on the ice and it can measure the bottom of the ice and how it's changing. So there was these peaks in melting that are highlighted here, where you get something like 15 to 20 meters a year of melt. They're happening again every 14 days because this was the site where those meltwater pulses were passing through. Same story, they're happening at neap tides. And when you look at this is now the temperature and the salinity in the boundary layer. These peaks are happening right before you have this big dive in temperature and salinity, where you're starting to cool and freshen the boundary layer. And so these peaks are actually leading it ever so slightly, so there's a front that's basically passing by. And if I have time later, I have like a zoom in of each one of them that shows it really nicely. But I did some fancy stuff, and I did the best I could to estimate the current speeds flowing past the site, as well as what was happening to the boundary salinity and temperature as these pulses swept past. So these peaks in melting were a result of basically a plume, a stronger, strengthened plume flowing past the site. And so the takeaway here is that, like, there's big changes in mixing that's happening that's resulting in these melt rates. And of course, this is affecting the way we're estimating or parameterizing melting. And if you're using a constant parameter to do this, you're just gonna like be totally wrong, right? So that was kind of where I got my start with it, and where I sort of developed a real interest for understanding that boundary layer mixing. It sort of takes me back to this figure from this paper here. I took all the ice observations with the camera and with the forward-looking sonar, and I measured all these different features that were there. And then I used our current speeds, and I calculated directly the friction velocity and backed out a drag coefficient and so on and so forth. And I produced these ranges in these parameters that modelers could then use in their model. And this was something I was quite proud of, because it's basically taking observations and making them truly useful for modeling. And this is like an interesting environment. You have sort of all sorts of different stuff in the ice, morphology, but you arrive at a similar drag coefficient despite that, but this is nearly unstratified. The change in temperature here is quite strong, so this is stratified, but everything in that crevasse was nearly the same temperature and salinity. So in this environment, you're not actually doing that much with density differences between the ice and the ocean, and you also have this sloping wall of ice. So it's helpful, but it's maybe not realistic when we start thinking about warming temperatures. So now I'm doing the same sort of thing from data collected beneath Thwaites Glacier, where you have here, this is the ice, these are these sort of terrace features I mentioned before, these step-like features. This is just a map showing what that terrace looks like. And these are the ADCP data, so currents in black to white, and these are all the little profiles from our robot, colored by distance in this about 200 meter long feature. And so here I'll just step through what we're seeing as quickly as I can to just sort of highlight how now I'm trying to do this in a way that's sort of more difficult, and it involves this sort of near boundary layer stratification. So I'm going to plot here, this is vertical profile of temperature, salinity, oxygen, all relative to the top of this terrace where this white line is the bottom of it. And then these are our favorite TS and DOS diagrams. And you'll see as you step through it, as you get into the middle of the terrace, you start to really accumulate a lot of this temperature, sort of cooler and fresher water. This is meltwater, which is oxygen rich. And that continues until you get towards the wall, where it then begins to break down. So you're actually mixing a lot of that meltwater up now. And then you have these incredible profiles where the robot was driven into the sidewall of the terrace. And this is resolving this tiny little thin boundary layer from the rising plume that's coming across it. And this white line in TS space is showing like a typical mixing between seawater and melted ice just due to turbulent mixing. And then when you get these tails here, it's telling us there's some breaking away from that. That's happening probably due to increased stratification. So just something else I'll highlight. There's these three different circulation patterns in this tiny little feature. The velocities are quite different depending on where you are there. And the circulation pattern itself is incredible. So this is plotting it as like a 3D plot. And you can see in this outer section out here, you have like a flow along the base of the terrace. And in the middle, you have something now that's moving, once we switch to that, that's moving now away from the wall of the terrace. And then underneath the corner of the terrace, you have a whole 360-degree rotation in the water column underneath the base of it. So all of this is just, it's really thick as far as content, and so I'm really trying to take my time to analyze these data to their utmost before I go any further with them. But it's just fascinating. I wish I was just left alone so I could work on stuff like this. So this is a video, in case the data didn't speak for themselves. This is the video of the data collection from the robot. So we're running into the ice on the roof, and this is now the base. And you can see it's this flat, featureless stuff, and then the wall is filled with these scallops, which represent the size of the turbulent eddies. But on the roof and the base, where you have a lot of stratification, you don't see those features. So they're telling you something about the mixing as well. And I'm working with Ken Zhao at Harvard he has a DNS model that he's run for this little section right here. And we're working on integrating my observations into the model to produce sort of a realistic melt rate. And also, since it's direct numerical simulations, he can fill out the 5 centimeters that the robot has between its nose and the CTD sensor. So he can truly resolve all the stuff that's going on there. So just future opportunities. In January of 2024, we sent a field team down to Fimble Ice Shelf in Antarctica. They drilled through here and collected a bunch of great data, and I submitted a proposal the following June to analyze those data, because NSF wouldn't pay for us to collect it, so we had to do it on our own dime. So we'll see what happens with that. There's an example of the rich data set that was collected there. It's in another one of these really big channels, and it's got all sorts of detail in the ice and then the ocean signals that are really rich and just it's just waiting to be analyzed. So summary: small-scale mixing processes control these heat and salt fluxes into the ice and the resulting melt rate, and that's really what's forcing the ice sheets to change from the ocean side. And we really need to start using these sort of observations and putting them into models in realistic ways so we can get a grasp on how the ice sheets are melting and then we can improve sea level rise projections. So the next 10 years, I think, for me, it involves crossing boundaries from the small scale to the fjord scale or shelf scale out into the open ocean. So here's a schematic from this paper below showing Greenland. The water that melts Greenland flows up from the Gulf Stream. So right next door, that same water that flows past South Florida makes its way up to Greenland. And it takes all these different flow paths to interact with the ice and then melt it, and then there's this resulting fresh water that dumps into the North Atlantic. So in the last 30 years, there's been this warming signal. This is the tropics, this is the North Atlantic, and this is now what's hitting the subpolar. So the water's warming, and the ice sheet and the glaciers are responding to it. In my 2018 paper here, I picked out the Atlantic water that was sitting all the way up here in the Arctic, in the Lincoln Sea, that was making its way over several sills and being modified and flowing under the ice shelf of Petermann Glacier there. So that water has warmed significantly over the 20 years of observations, about 0.2 or so degrees, maybe a bit more. And then the grounding line of the glacier was stable for a really long time, but then it started jumping back all of a sudden. And this just points to us not fully understanding how the ice and ocean are interacting there. So this is fresh data from a couple weeks ago in Wissenholm Fjord, Greenland. This is what the fjord, this is like a cross section going across the fjord, the main inflow and outflow into the fjord. And that's the ocean temperatures in 2017 when I first collected data there. And this is what it looked like in 2025. And there was a 2-degree warming in 8 years. And the glaciers, of course, are just marching back there as well. So we really need to monitor, and we need to understand how the ocean is melting the ice there. So for Antarctica, we really don't have a good grasp on how these huge ice shelves are melting. This is like a really amazing study that used remote sensing and combined it with all the existing published ocean data that was in the World Ocean Database, maybe that's what it's called, around Antarctica, and measured the melt rates around the ice shelves around Antarctica. But when you zoom into one of the large ones here, and you compare those remotely sensed melt rates, which are it's an altimetry measurement. It's basically seeing how the surface is changing over time. And when you compare it to actual on-the-site measurements from a phase-sensitive radar, the altimetry is suggesting large freezing, so accumulation on the bottom of the ice, when in fact there's actually weak melting. So this just points out that we need better measurements to improve our models to understand how these huge ice shelves are melting and will change. So just looking and summarizing our long-term research interests, our sustained monitoring of these fjords in Greenland. We need space and time, so this includes gliders, moorings, shipboard or snowmobile surveys, and then of course any sort of acoustics that you can use to transmit over larger distances. I think the ice-ocean interface is still a really important problem. I think novel tools like IceFin, the underwater robotic I'm using right now, are the right tools to use to study this interface. And then we need to connect these scales. So for Greenland, it's connecting to the North Atlantic. For Antarctica, it's connecting to the Southern Ocean. And I know some people in the room here do that sort of work, and it's something I'm really interested in, sort of collaborating and applying my small scale or fjord scale stuff into the larger scales. And then of course we need to integrate observations in the models. And then for me, honestly, the opportunity to connect this work at the poles, which is very far away, heavy logistics, to localized research in estuaries, to me is an amazing opportunity and something I'd be really interested in. And so these are just a few of the teaching opportunities that I could see myself being interested in here as well. And I'll just conclude with this slide. I think it's important for us in this room to understand how the sea is rising. I think I have things to say about that, and I think my research certainly has applications to what's happening in South Florida. So if we can better understand where South Florida is going to be before 2100, we can talk to policymakers that can then prepare for it. And I'll conclude there and take any questions.
Thank you, Peter. That was really interesting. Are there any questions?
Yeah, I have one. I mean, thank you for the talk. I learned it a lot. I don't know anything about, but I was actually thinking a lot. One of your last conclusions says, like, fjords with estuaries, kind of we know from basic oceanography, like relation. But when I was seeing the movies and pictures and seeing the differences in how the ice, like lines or more different forms, I was actually thinking on sediments on different current situations, right? Like coastal, and I wonder if there is any relation, people that work with ice and sediments, and
Yeah, so the way you get a drag coefficient for ice is, and the way you relate that to the wavelength of these features is directly related to the way you do it with sediment.
With sediment, yeah.
So it started with like the paper, there's one from the 70s that published, I think it's a Reynolds number, maybe. I can't remember off the top of my head, but it comes from cave research and like rock walls that are being eroded. But yeah, I mean, the current direction, the sort of, and how things are organized are a result of currents. So yeah, it's similar.
Another question, I'm sorry. The first figure you show with the sea level rise, I think you mentioned was from a proposal, but is there any paper about it? Like the rate of melt with the stratification?
No, my boss is on my back to turn that into paper. I think it's a little oversimplified for me to be comfortable submitting it as a manuscript, so I want to do a little more work on it. But for a proposal, I think it really hopefully sells the point.
I mean, I was wondering about the calculation because one of the experiments I do with the undergrads for convection is melting, and we do different salinities. So I was curious to see if there was a real paper about it.
Yeah, so it's based off the 3-equation melt parameterization.
Okay, I don't know anything about
it. It's
my
conservation of
is more basic, but anyway,
conservation of heat and salt. Yeah.
Right.
I have a related question. So the bottom in those areas, I guess, what is the roughness? Is it just ground flat from all the glaciers?
Oh, the seabed. The seabed.
Yeah.
It's really variable because once you at the grounding line or in the grounding zone, it's quite rough, and there's a lot of sort of ridging, especially when you have a retreating grounding line, which is tidally modulated. You get really interesting features. We have a multi-beam that flips up and down. That data's it's there. It's good. I just haven't got to work with it so much. But yeah, and then as you move away from, if you move further away from the grounding line, but still close enough, you get a lot of rain out of sediment. So then it gets covered, the bed, and it looks more like sort of abyssal plains and stuff.
Thank you for your interesting talk, fascinating science. I have a question about the connection that you mentioned between the large scale and the smaller scale melt processes. So you mentioned that there's meridional overturning, water masses involved in meridional overturning circulation are getting warmer, but the overturning is also slowing down.
Yeah.
So how do you balance this?
I think probably that was picked at a different point. If you were to move from America to Europe, because yes, certainly the North Atlantic meridional overturning circulation is slowing down due to fresh water, right? And it's actually, I think, cooling in many locations. I think that was just more showing, probably it was picked in the Gulf Stream, and it was showing the heat transport up to Greenland.
Okay.
So, but then you're right, there's an interplay where as you melt more, you dump more fresh water, and you stratify the surface of the North Atlantic. So.
Thank you.
Are people working on the problem of what happens to the water once it melts and how does it spread in the ocean circulation? I never hear about it.
Yeah, certainly. So,
In terms of sea level rise.
oh, I see.
I mean, let's say something melted so many tons. I mean, does it stay local? Is it coming to Miami? Who is working on this problem?
Yeah, I mean, I can speak to the local of the fjord scale. So, like, during my PhD, did this sort of once you melt, what happens? How's the local circulation change? And it is exported, the fresh water. Once it leaves the fjord, it catches whatever coastal circulation, and then it comes back down.
Because the ocean circulation has its own.
Yes, it's not
Which is
global
huge.
means sea
Yeah.
level. It doesn't all actually come up just like this.
Exactly.
Yeah, so I would say people are working on that. It's not my area of expertise, but on the sort of fjord scale, it's something I'm interested in. So
Very nice.
flux is right. Thank you.
I have a couple of questions. Do you want to go first, or?
Sure. Yeah, so thank you. I have a question about the slide you showed in 5 and 22, and it is the slide where you showed the melt rate with lower bound and upper bound. And the question, and then you also mentioned that in different temperature and salinity, what will be the melt rate, like for future projections. And it is very interesting because the uncertainty, like the sea level uncertainty we got from climate models, we have large uncertainty, and it's a big challenge to reduce that uncertainty. And most of the uncertainty comes from this IC modeling. The question is, how your work gonna reduce that melt rate spread? You mentioned in that slide, because you mentioned in one of your slides showed you computed the melt rate based on your observation, and I'm sure the picture you showed, that also the rate also comes from some observation. So I'm thinking like how you gonna feed that, how you gonna reduce that?
So I mean, first and foremost, once you get the observation and you resolve the physics as well as possible, when you can boil it down to these coefficients that are based on a local sort of setting, then you have something that represents the temperature and salinity that a model might use in that location. So before I started working on this problem, all of those data came from cold, unstratified environments. Basically, heat and salt go right into the ice. There's no problem. I started working on it, and I started working in warmer environments where there was stratification, and that density difference was then inhibiting the mixing. So that was during my PhD. I backed out those coefficients and then produced the lower bound of that plot. So without what I had done, there would have only been that upper bound. And so we wouldn't have had that spread to begin with. So you would have overestimated melting that. But then with the stuff from the crevasse, I basically went into a cold environment and confirmed that the existing parameterizations in that environment worked with observations, but it did it in a crevasse, not on a flat piece of ice, which shows, okay, in a cold environment, ice that's flat melts at the same rate that ice melts that is sloped. Now what I'm working on now with the Thwaites Glacier stuff is you take a warm environment that has both flat ice and sloped ice, and you look at how it melts in these different scenarios, because if you have flat ice and you melt, you create a freshwater lens, there's a density interface that's going to reduce mixing and therefore melting. But you put a slope on it, and then you have a rising plume that can destratify, and then that will melt differently. So that's kind of like what I'm working on now. The Nature paper I showed earlier on Thwaites basically did a first order thing at doing this, but now I would like to go back and get the physics right as much as possible.
Thank you.
So I hope that answers.
So if I understand, the point is the estimates you showed that maybe the data they use is maybe less reliable than the data you are using now, right? It's more because it's more present data, and you said it's getting the both conditions warm and cold, right?
Yeah, warm and cold, as well as ice. If ice is flat or sloped, and doing that on small scale hopefully can translate into, if you create an ice sheet or an ice shelf in a model, you can nest some roughness in it on sort of an average sense. Because you only have to get this right on the size of grid cell, right, in a model to make it more realistic. So you could sweep a parameter sweep basically from one point of the ice shelf to the other point as you're moving away from the grounding line and say this is how that might change as you move up.
And another question, so you think, because you already published this paper in Nature, so the modeling community are moving to graph the new numbers you mentioned? Because
there are conversations I'm having, and I get oftentimes the answers are like, yeah, okay, that's good. But we have these projects we're working on, and maybe in the next round we can start doing that. But I am, my collaborator Ken Zhao, he runs DNS models all the way out to GCMs, global circulation models. So if him and I can work on this direct numerical simulation and get this stuff pinned down there, then you could maybe step out from there. So it's something, I mean, I have the results in a slide that follows. So he's already run the DNS and it looks pretty good. So yeah, it's not an easy task, right? And it's easier for me to create the data than maybe it is for modelers to implement it, but it's what I can do. Thank you.
I have some questions, a couple questions. So I find these upside down crevasses really interesting. Can you say, I was thinking about whether that situation, you showed this overturning and you said that it was driven by actually freezing, brine rejection. And then presumably if you set up an overturning, then you could get some feedback, I guess, depending on how deep that overturning reaches beneath the ice and things like that. But do you have any, what's your thinking on, first of all, how these crevasses are formed and how much that setup of overturning, affects them, forms them, modifies them? And then do you think it's a stable situation or an unstable? In other words, if then because it occurs to me, if you introduce seawater in this estuarine underneath, and you reach down to that, presumably that's a negative feedback on the freezing, right? So I don't know, do you think these crevasses are going to get bigger or smaller as we get warm water intruding? And do you think that is going to, how do you think that's going to affect the melting?
Yeah, so the one with the overturning circulation was in a cold environment. That is a really interesting setting because basically the ice flowing into the ocean has stopped there because the ice stream has then frozen to bed. It's this bizarre scenario, but the ice is just simply stretching the part that's in the ocean from there, and it's cracked. So as ice moves across the grounding line, there's like a good bit of stress that turns into strain, and you crack these crevasses. But in that environment, you can see the frozen seawater, which we call marine ice, in this environment actually attaching to the walls in these sort of clumps. So it's filling in to some extent at the top. But actually, what I didn't show, there's this cool thing with the tide there where you actually move more heat into the crevasse during springs and less during neaps, as far as we can tell. So that is probably like an almost sort of steady state feature, where you're freezing and then you're probably melting a little whatever you're froze during the neaps, during the springs, and it just sort of stays there, and it's only moving forward 5 meters a year into the ocean. But the Thwaites crevasses are 3 times the width. So they're like, you put one of these crevasses in a warm environment and they just melt like crazy. So they crack, they move forward, and then the ocean modifies them by melting them out, and then they create those huge rifts you see in the surface of the ice, because once they melt to some extent, they weaken that section of the ice shelf to the point that it can then break. And there's like some pretty cool theory papers on this that show like under this amount of ocean modification, a crevasse becomes unstable and then weakens the ice shelf. And if it remains cold long enough and it's advected seaward, it eventually can freeze back in. If it moves into, as you move up in the water column in Antarctica, the water cools, right? So you could totally fill it in if it stayed really cold. So yeah, but for me, I mean, as an oceanographer, it was just great to see like there's these sort of coastal circulation patterns that are moving in the Y direction, and it's not just a back and forth, which is kind of how we generally had thought about it. So.
Right. My second question was, you didn't really talk about the additional, I mean, you talked about the horizontal versus vertical or sloping interface. You've also got a lot more surface area.
Yes, in the horizontal especially.
Right, so you've got much more boundary layer going on. What does that mean to you, if anything, in terms of how you think that might be affecting the circulation?
Yeah, it's a good question. So freshwater is buoyant. It's going to find whatever it can find to get up in the water column. So if you had like a large, just flat sheet of ice, then it would just sit, right? But if it can be moved in some way to a point where it can go up, it will want to do that. So then you would have to have some sort of circulation patterns that were moving it away. But on like a scale of like what we've been observing, I don't know if I can really say if you're melting more at the base of the ice and it's just sitting there, how that small scale density difference, unless you had a background slope moving in one direction, is going to affect the larger circulation. But I think if you have a slight tilt in the ice, and from what I can see, nothing's really flat, it's only like flat for a bit, there's probably a slope somewhere that then can drive density differences. And then I hesitate to say anything's really geostrophic here, but I think certainly the baroclinic circulation is evident in these data. So, not a direct answer, I'm sorry, but it's the best I can do right now.
Any more questions? Okay, thank you very much.
Yeah, thanks for coming.